Discover how to build an intelligent book recommendation system using the power of large language models and Python. Learn to transform book descriptions into mathematical representations that enable precise content-based matching. By the end of this course, you'll have built a recommendation engine that helps readers discover their next favorite book. Dr. Jodie from JetBrains developed this course. JetBrains provided a grant to make this course possible.
Would you like to get started using large language models for your own project, but you don't know where to start? With technical sounding terms like semantic similarity, vector search, and zero-shot classification, the area can feel very unapproachable from the outside. However, in this tutorial, I'm going to show you how working with LLMs is a lot more straightforward than you might think. In this tutorial, I'm going to show you how to build a book recommender using some of the most cutting-edge techniques in natural language processing. Using LLMs at almost every stage, I'm going to show you how to clean and prepare text data, how to use vector search to find the most similar books to a query, how to use large language models to find the topic of a book, and also how to find the emotional tone of a book using LLMs. And then finally, we're going to bundle all of this up into a dashboard so people can actually get their book recommendations. Before introducing any new concepts, I will take you through a little bit of theory so you can understand what's happening under the hood. But otherwise, this is going to be a very hands-on, code-driven tutorial, which is going to allow you to develop your very own semantic book recommender. So in order to get the most out of this course, I would recommend it for people who have some experience with Python and know the basics of machine learning. But you don't really need to know anything about deep learning or natural language processing in order to follow the materials. Finally, I hope you'll be able to see that what we cover in this tutorial has a lot of applications for working with text more broadly. Of course, you can take what we learn about building a book recommender and build a recommender for anything that involves text, things like movies or products. But you'll also be able to take the individual components, things like text classification and vector search, and apply them to a wide variety of natural language processing projects. Before we get started, I'd also like to briefly introduce myself. My name is Jodie Birchall, and I've been working as a data scientist, particularly in the area of natural language processing, for almost 10 years now. I'm currently working at JetBrains, a company well known for creating development tools, and we're going to be seeing one of those tools today, PyCharm, which is an IDE which has some really great features for working with data science projects and also working with large language models. If you'd like to reach out with some questions or comments about this tutorial, my social media links are in the description of this video, and I'm also going to share some other content you might find interesting in the area of natural language processing that I've also created. With all of that covered, let's get started. So we're going to start this project in the exact same place that we start any data science project, and that is, of course, by getting some data. So we're going to be getting data today from one of my favorite sources, and this is Kaggle datasets. So Kaggle has this fantastic subsection which hosts a whole bunch of really interesting datasets. We can get to that by going to kaggle.com/datasets, as you can see here. Now, the really interesting thing about this is a lot of these datasets were created by members of the community, and they've generously uploaded those for all of us to use in our projects. And something else you can see is that NLP is one of the specific tags. So there are a whole bunch of really interesting NLP datasets. You can see these here. We, of course, want to do something very specific today. We want to have a look at datasets that have to do with books. So we're just going to click out of that tag, and we're going to specifically search for books datasets. And what we found here is the dataset that I have already looked for that I want to work with for this project, and that's the 7K books dataset. So if we go to the page of this dataset and we scroll down to where the dataset is described, we can see that there are a whole bunch of really interesting columns that we can use for our recommender. So we have, of course, the ISBN, the book identifier. We've got the title and subtitle of each book and who wrote it, the authors. We've got the categories of the book. We've got a thumbnail of the front cover that we might be able to use later, a description of the book, and then additional fields like when it was published and what the rating is. So now that we have this lovely data set, let's talk about how we're going to work with it. And the tool we're going to be using to work with this data is PyCharm. So PyCharm is an all-in-one Python IDE, and it gives you a huge range of functionality for working with Python including in data science, and as we'll see later, specifically for working with large language models. So if you want to follow along with me and have all of the same functionality that I do, you can, of course, download a copy of PyCharm if you don't have it already. So just pop over to the PyCharm landing page at jetbrains.com/PyCharm/data science, and you'll see we have the button here to download it. Now, for viewers of this video, we're actually offering an extended 3-month trial of PyCharm Professional. So if you pop down to the description section, you'll see that promo code there. And then if you pop over to jetbrains.com/store/redeem, you'll see you have the option to redeem it there. So if you don't already have PyCharm and you want to follow along, just pause this video, go do that, and then we'll get started in the next section. So once we've installed PyCharm, we can, of course, open it just by clicking on the icon in the dock here on Mac. And what you can see is this then lands us on the welcoming screen. So PyCharm's welcome screen shows you the most recent projects that you've worked on, and it also gives you a quick way of either starting a new project or even just quickly starting a new notebook or a new script if you want to get started a little bit faster. So we're going to start a new project because we know that we're going to be doing quite a lot of work. So we click on New Project, and what this then takes us to is a loading screen in order to create this new project. And we have a few different options for project types, as you can see over in the left-hand side. So because we're working on a scientific Python project, a Jupyter-based project, we do have the option of creating a Jupyter-based project. And what this does is default to an Anaconda interpreter. And it also gives us, a bunch of other things that are sort of set up in the project structure, like assuming that we have data and gives us folders for that. But I have a preference for using virtual environments. So I'm actually just going to stick with a pure Python project. And what you can see is that gives us the option of a few different interpreter types. So virtual environments, Anaconda, and we can also create other types of interpreters. So just leaving it as the default for virtual environment. And now I'm going to name that project, and we're going to call it Book Recommender, big surprise. And then once I've given it a name, we can just click create and it will go ahead and make that project for us. So PyCharm has now gone ahead and created that new project for us. And if we go down to the right-hand corner, we can see that it has set up that new interpreter for us as requested. Set up a 311 interpreter for me because that's my system default, but you have the option to play around with different interpreters if you would like when you set up your project. And you can also see if we go across to this Python packages tool window, that it's set up a fresh virtual environment as requested. So we just have the basic packages installed and it's ready for us to install our packages. So we're now going to use this Python packages tool window in order to install all of the dependencies we need for our project. So the first library that we're going to install is called Kaggle Hub. This gives us a really convenient way of interfacing with data that we might want to use from Kaggle. So rather than having to manually download it, this gives us a really nice way of managing downloading that data. The next we're going to install is Pandas. Pandas, I think, needs no introduction, but basically it's going to give us a really convenient way of working with that tabular data that we're going to be downloading from Kaggle. And then for visualization, we're going to be using Matplotlib, and we're also going to be using Seaborn. So you can use whatever graphing package you like. I just have my preferences. Seaborn is my favorite, and Matplotlib is a dependency for that. But, whatever graphing packages you want to use, you can, of course, use. Then we're going to also be working with some credentials. We're going to be working with some models from OpenAI, and that's going to require an API key. So a nice package that I found for working with this is called python.env. So that's the next thing we're going to install. And then we need some packages for working with large language models. So the first of these is a framework called LangChain. And we're going to go into this a bit more in the next section. But LangChain is essentially a collection of packages which is designed for doing all sorts of stuff for working with large language models. So LangChain is going to be really useful for when we need to create the recommender. We're going to see how to use that again, as I said, more in the next section. But LangChain is basically broken down into a number of different packages. We're going to be installing 3. We're going to be installing one called LangChain Community. We're also going to be installing one called LangChain OpenAI for working with the OpenAI model, as I said. And then we're also going to be installing one called LangChain Chroma, and this is for working with a vector database. So having installed all of these, we can move on to our last few packages. The next important package for working with large language models is Transformers. And Transformers is a really powerful package from Hugging Face, which is designed for working with open source large language models. And again, later in this video, we're going to see more of how you can work with Transformers, but this is a very powerful package as well, and it gives you a lot of options for working with LLMs. We are also going to be presenting our results or allowing people to interact with our recommender through a dashboard. So we're going to be using a framework called Gradio for that. And we're just going to install this here. And then finally, of course, we're working with a Jupyter notebook. So we're going to go ahead and install Jupyter and also IPy widgets. So that's everything. We've set up all of our dependencies for this project. If you're following along, you can also install these here at this stage. And that means that the project's going to run smoothly for you as we work through the tutorial. So with all of that set up, we are finally ready to start working with our data. So first things first, we're going to create a fresh Jupyter notebook. So we do this by right-clicking on the project name, going to New, and going to Jupyter Notebook. And this is going to open up a new Jupyter notebook for us. And remember I mentioned that we were downloading the Kaggle Hub library, and you may be wondering what we were going to use that for. Well, if we go back to the page where our data set is on Kaggle, and we go to this download button in the right top corner, what we can see is that it actually gives us this ability to download using this Kaggle Hub package, and it gives us some template Python code that we can use. So we copy that code, go back over to our Jupyter notebook and paste that in. What we can see is that it's given us a path where it's automatically in the background downloaded that data for us. So let's now explore this directory that Kaggle Hub has created for us. So let's copy this path, and we're going to open a new terminal window. And within that terminal, we're going to navigate to that directory. And if we use ls to have a look at what's in that directory, we can see that what Kaggle Hub has downloaded for us is one file, books.csv, and this is our entire data set. So this actually makes life easier for us because we don't need to merge or combine anything. So now that we have the location of the data, we can read it into pandas. So of course, we import pandas as PD. And then what we do is we use the pandas read CSV method. We're going to change that into an F string. And then what we're going to do is insert that path and combine that with the book CSV file. So once we do that, we can have a look at our file and voila, we can see that exact data that we saw on Kaggle read into a pandas data frame and ready for us to work with. So I think all of the hype around large language models has sort of given the impression that working with text data or these NLP projects are really distinct from other types of data science or machine learning work. But they're really not. They're actually, they have all of the same problems as other type of data science projects. And of course, what that means is the first step is inspecting the data. So let's have a look firstly at the data frame that we've just read in. And we had a quick look at this when we had a look at the Kaggle page, but let's just have a look through it again. So what we can see is we've got a number of really useful columns. We've got our identifiers, our ISBNs. We've got the title and subtitle of the book. We've got who wrote it, and we've got the category of the book. And we've got that description field, which we've already pegged is likely to be pretty much the most useful information we have about the book, telling us why people might like it, why we can recommend it. Then we can see we've got a number of other really interesting fields. We've got the year that the book was published. We've got the average rating. We've got the number of pages, and we've got the number of ratings. So we've got a lot of really good information here to start on our project. So let's now have a closer look at the data. And this is usually the stage in any data science project where we'd be writing a bunch of boilerplate code in order to get the relevant descriptive statistics. But luckily, PyCharm gives us a way to shortcut this because it is quite boring. And what we can do is we can use a feature in the interactive data frames called Show Column Statistics. So if we click on this button, what we can see is we have a couple of different options. I'm going to pick Detailed. And what you can see is the Detailed gives us the relevant statistics for each data type above each column, so whether it's categorical or continuous. So let's have a look at the information that this has given us. So the first piece of information that jumps out is that we have 6,810 books. And if we have a look at the ISBN 10 column, we can actually see that these are distinct. So we have all of these entries are unique, and it means we're not going to need to do any deduplication. The second thing that jumps out is if we go over to the subtitle column, we can see that it has a lot of missing observations. So probably 2/3 of the observations are missing. And this really makes this column useless in and of itself. We can't really use it by itself. So we're going to have to get creative and think about how we might be able to use it if we want to keep hold of that information. The next thing that we can notice is with the categories column. If we have a look at the number of distinct observations, there are a lot of different categories. And we've already kind of seen that, if you actually look at the column, you can see that it has really useless looking categories like Heinlein horn. These are not really useful categories. So we're probably going to need to clean this and standardize it in some way in order to make it useful because we potentially want to use it as part of our recommender, and we don't want to have hundreds of different categories for people to pick from. And then finally, let's have a look at our most important column, the description column. And we can see that we only have description missing for around 4% of books. So this is pretty good, but we should do some deeper investigation just to check whether, this missingness is not biased in some way. So it's really important to check whether missing values have a pattern, because this can imply some sort of bias if you find that the missing values are linked to particular characteristics about, say, the books that we have in our data set. So my favorite way of doing this is by creating a missingness heat map using Seaborn. This is pretty easy to create. So of course, the first thing we need to do is import our dependencies. So we import Seaborn and we import matplotlib pyplot. And then once we've done that, we instantiate our matplotlib plot. And then what we do is we tell matplotlib that that is going to be a Seaborn heat map. And we're going to change this so it is a heat map, which documents all of the different missing values, the is NA values. And we're going to transpose that just to make it a bit nicer for the display. Now that we've done that, we are going to add some labels. So we're going to add the X label columns. So that's all of our fields or our variables in our data set. And we are also going to add a Y label for the missing values. And then we just need to display that plot. So this gives us a really interesting picture. What you can see is that, as we saw in the descriptive statistics, subtitle is mostly missing. So we can kind of write that variable off, but we already knew that. We can see that for the middle variables, so categories, thumbnails, and description, it's mostly looking random. But if we look at the three bottom variables, average rating, number of pages, and rating count, we can see that there's actually a clear pattern here, that observations that have one of them missing have all of them missing. So what we can kind of conclude from this is that these are probably from another data set, and that data set didn't contain all of the books in the bigger books data set. So this may potentially be a source of bias because maybe the books that are missing are, missing because they're newer or because they have other characteristics. Maybe they are better rated or worse rated. So this is something that we're going to check out next. So the final thing we're going to do with missingness is we're going to take a closer look at those books where the description is missing. And this is really important because this is really the core field that we're going to be using for all the natural language processing work going forward. So it's important to know whether there's any bias in the type of descriptions that we have missing, because we're going to be getting rid of these books. And we need to know whether our recommender will then skew towards certain types of books. So we have these really nice descriptive fields. We have the year that the book was published, we have the number of pages that the book has, and we have the average rating of the book. So we can use this to deduce things like, are books that have missing descriptions more likely to be older or more likely to be shorter? So in order to do this, the first thing we're going to do is create a numeric representation of which books are missing. So we're going to use NumPy's where method. And what we're doing is basically saying books where the description is missing, put a 1 in that column. If it's not missing, put a 0. Then what we're going to do is convert the year of the book into the age of the book. So we're going to take the year 2024 and subtract that book year. And let's run that. Now we can see that we've made a mistake with the name of the variable. So let's just correct that and run it again. And that's worked now. What we do is we create a list with just the subset of columns that we want from our books data set. So we want the number of pages, we want the age of the book, we want the missing description, and we want the average rating. Then what we do is we basically create a correlation matrix directly off the pandas data frame using just those columns. And you can see I've changed it to method equals Spearman rather than Pearson. Just as an aside, if you're interested in the statistics behind this, Pearson correlations are more appropriate when you're dealing with completely continuous variables. But as you can see, the missing description field is binary. So Spearman is just a more appropriate correlation coefficient when you're dealing with non-continuous values. Okay, so we have our correlation matrix. Now what we're going to do is convert that into a Seaborn heat map. So basically we set up the theme and the figure, and then what we do is we create the heat map, pass over the correlation matrix, put in some formatting things such as the number of decimal places, the color scheme, and also the labeling. We set the title of that heat map, and then we show it. So let's now have a closer look at this heat map. And really what we're interested in, as I said, is this missing description correlation with the other variables. We want to know whether any of these variables have a high correlation with missing description. And the reason we want to know this is, say number of pages was correlated with missing description. It would indicate that either longer books or shorter books had a missing description. And as you'll see, we're not going to use the books that have a missing description. So it means that our recommender may be biased towards shorter or longer books. Same as with the age of the book and with the average rating. But if we have a look at these values, you can see that they're really not very strong. And just to kind of give some context for those of you who are not used to interpreting correlation coefficients, anything that's close to 1 or -1 is a really strong correlation. Anything that's closer to 0 is a very weak correlation. It indicates there's not really a relationship. So you can see there's nothing really there. And what this gives us is a bit of confidence that, at least in terms of these dimensions, our book descriptions are pretty representative. So we're going to have a pretty good range of older books, of books with a good range of ratings and good range of lengths in terms of what we can give our users of our recommender. So because we have a small number of observations with missing values, because there doesn't really seem to be a pattern in terms of the missingness, and because replacing these descriptions is going to be a pain in the butt, it's probably going to involve a lot of web scraping to retrieve the actual description, I think it's safe for us to just delete those observations with missing values. So first things first, let's do our due diligence and find out how many books that's going to cost us. So what we can do is do a bit of conditional logic using pandas. And what we want to know is those books that are going to have a missing description, that are going to have missing number of pages, a missing average rating, and also a missing published year. So you can see that this conditional logic is basically saying if it is missing in description or it's missing a number of pages, etc., please fetch me all of those observations. So we look at the resulting data frame. What we can see is this consists of 303 rows, which, given the size of our data set, this is well under 5%. So we can definitely go ahead and get rid of these observations and not stress too much. So let's now create a new data frame, which is going to remove these missing observations. So we're going to call it book missing. And we're just going to modify this conditional logic so that it is the opposite of what we just created. We want to keep all of these observations that don't have these fields missing. So what we'll do is add a negation to the front of each of the conditions, and we'll just change those ors to ands. And voila, we have our new data frame, which has only those books that have all of those fields with complete values. So the next thing I'm going to do is revisit that categories field. And just to remind you, the problem we had with the categories field is it just had way too many distinct values. So it's kind of unusable in its current form. So first things first, let's enable the column statistics again and check what it looks like after we deleted the missing observations. And we can see that, well, it's still a mess. We still have over 500 different categories, but it probably wasn't going to solve the problem because we only deleted 300 or so observations. So let's just have a look at the type of categories that we have. And we can see, there are some that are very, very specific, like Highland Morn. I'm guessing that this is probably one of the characters in the book. And this is just so specific. No one's going to use this as a category. So let's have a closer look at the distribution of categories. And so the way we can do this is by taking the value counts of each of the categories. And I'm just going to add a bit more code just to make this a bit easier for us to visualize. So I'm going to reset the index so that all of the categories are put back into a column. And I'm going to sort the values by count, and I'm going to sort it by descending. So what we have is basically the categories that are most popular at the top and those that are the least popular at the bottom. So if we look at the resulting table, you can already see we really have a very uneven distribution of categories. So fiction is the most popular, juvenile fiction is next, and then it just sort of keeps going down into more and more specific fields. But to really get a handle on how uneven this distribution is, let's visualize it. So we'll visualize it as essentially a bar chart showing the counts of each of these. And so we can use this really handy function that belongs to data frames inside PyCharm. So we go up to this button and click Chart View. What we then switch over is to a no-code panel that allows us to do visualizations directly off the data frame without having to write any code. So if we go over to the settings, what we can do is change the y-axis to count, and then we can change the type of chart to bar. And this gives us a really good indication of just how uneven that distribution is. So we can see that if we hover over it, it really doesn't take very long until we start getting to categories that only have one or two actual books contained within them. So this shows us really we have a long tail problem with book category, and we really, really need to focus on how we're going to normalize that. So that's actually going to be one of the sections of this video. I'm going to show you how to do this using large language models, and this will be a way of introducing you to text classification and how you can do this using very modern tools. So the final thing that we're going to do in terms of cleaning and screening this data is just having a closer look at that descriptions category and seeing whether there's a way to potentially refine it a bit more. So the really important thing about the descriptions category is that it needs to be meaningful. It needs to contain enough information about what the book is about so that we can recommend it, because if it's not in the description, it's not going to be anywhere. So let's have a look at our new data frame, the book missing one. And if we scroll over to the description column, what we can see immediately in the top 10 is a completely useless description. We can see this on the 7th row where it says donation. So this is obviously not going to be a helpful description, and we want to get rid of ones like this. So the easiest way to actually identify these is by checking how long they are. This has one word, so it's probably not going to be a useful description. So what we're going to do is create a bit of code. And the first thing that we're going to do is, we can see that PyCharm has already completed that for me. But basically what we're going to do is create a new variable called words in description. And what we're going to do is take the description, split it based on space. This is the default 4-string split. And then what we're going to do is ask for the length of that list that results from splitting that string. And what that would give us is a count of the number of words. So we've assigned this to a new variable. So again, let's look at the data frame, and you can see that we have, a pretty good distribution of the words in the description. And you can see there again on row 7, our donation one, the one with 1 word. So again, let's visualize this. We're going to use the chart view functionality again. And what we're going to do is we're going to switch over to histogram. And then we're going to assign the words in description variable to both the X and the Y axis. And we'll just change this to count on the Y axis. So what you can see is we have actually a pretty, even distribution of the number of words in the description between, probably about 10 or maybe a little bit higher up to around 200 or 300. So what this means is there's not really a natural breakpoint where there are a clear group of descriptions that are really short and are maybe, donation or something like that, and those that are a bit longer and more meaningful. So what this means is we're going to need to create an arbitrary cut point ourselves. So a relatively straightforward way of working out where this cutoff will be, how many words a description needs to have in order to be meaningful, is just come up with some cutoffs, come up with some bins for how many words the description needs to have, inspect the descriptions that have those number of words, and then, it's really just a gut feeling for whether you think that this gives you enough information to know what the book is about. So what we're going to do is create some pandas code, and we're going to filter the pandas data frame so that we have all of those books where the words in description are between 1 and 4 to start. So this is going to be our smallest group, and we really just want to return the descriptions. So that's what we're going to put in the second part of the conditional. And when we run that, what we find is, yes, indeed, these are all completely useless. First published in 1813, edited by Maurice Hindle, no marketing blurb, fantasy roman, these are not very helpful. So basically, we can, I think, skip this and decide that this is definitely too small, no big surprise. So let's move up to the next bin, and I've decided on between 5 and 14 words. And again, this is really just a bit too short. A Matter of Life and Death and the Throne of England. A title story in this collection of shorts and now a film from Ang Lee. This is really not giving us particularly good information. So let's now move up to the next bin. And this one will be between 15 and 24. And you can see we're actually starting to get to a point where these are becoming meaningful. Like, a boy imagines what it would be like if he had things such as duck feet, or, a magical and fantastical collection of early stories. Still probably not enough though. So let's go up to the next bin. This is actually, spoiler alert, going to be the final bin that we look at. And what you see is, well and truly, now we're at a point where we have enough information. It would be the most natural thing in the world, but in Tony Parsons' latest bestseller, 3 couples discover that Mother Nature, blah, blah, blah. So this is really where we're starting to get to the point where it seems like there's enough information. So I think it's reasonable to use 25 words and up in the description as a cutoff. And now we need to really see what the impact of that is going to be. So let's now create some filtering code to clean up the data set again and remove all of those that have less than 25 words in the description. So again, we are going to create a new data frame called book missing 25 words. And we're going to filter, obviously, book missing. And this will be all of those rows where words in description are more than or equal to 25. So we're going to keep those. And then when we create that, let's go ahead and see how many rows that actually contains. And we can see that it contains around 5,200. So we have lost quite a lot of books as part of this filtering, but essentially we wouldn't have been able to use them anyway unless we replace those descriptions. So 5,000 is still a pretty good number, and I think we can be happy with that as the basis of our recommender. Okay, so there are a couple of final variables that we want to create before we declare that cleaning and screening is completely done. So the first thing is we need to decide what we're going to do with the subtitle field. So as we've already established, it's unusable on its own because there are so many missing values. But it's quite common to have a convention of books paired with their title and subtitle. So say Spider's Web : a novel would be, a pretty normal convention. Or Empires of the Monsoon : a history of the Indian Ocean and its invaders. So what we can do is create a new field called title and subtitle. And what we can do is we can actually pair the two if it exists. So again, we're going to use np-where. So first we start typing in for those where the subtitle is missing. We add the np-where clause. And what we do is we specify that when book's missing, or when subtitle is missing, please just use the title. But when it is present, when there is a subtitle, what we want you to do is to aggregate the title and subtitle. And we need to convert that explicitly to a string because there are a lot of missing values and they're considered as a float in pandas. We can join them using a colon, and voila, this has done the job. So let's go and have a look. And what we can see is we have this lovely new column which contains the title and subtitle, and it looks very good. Now, the last thing we want to do is we want to create a new description column which tags each description with a unique identifier. And I'm going to explain why we need to do this in the next section. You'll see why it'll be important for building the vector database. But for now, just trust me on it and I'll explain soon. So we can use either of the ISBN fields for this because we know that they're unique identifiers. I'm going to use the ISBN 13. And essentially, we're going to do a very similar thing that we did to create the title and subtitle. We're going to create a new variable called tag description. And what we're going to do is take the ISBN 13 and the description. Again, we're going to explicitly convert them both to string. And then what we're going to do is join them so that the ISBN is just attached as the first word of the description. So now that we've done that, again, let's have a look. And what we can see is that we have successfully created that column. So that's it. We have completely cleaned up the data set. It is now ready for all of the NLP work we want to do with it. So we're now ready to save it to file and use it for the rest of our project. So what we're going to do is drop some of those columns that we created that we don't need. We're going to drop the subtitle column, the missing description column, the age of book column, and the words in description column because we don't need them anymore. We just use them for cleaning or for filtering. And then what we're going to do is just save that to CSV. We're going to call it books cleaned CSV, and we're not going to save the index because we don't need it. And that's it. Now we have prepared everything. We've gotten all the boring stuff out of the way. We've eaten our vegetables, and now we're ready to get into the fun NLP stuff. So now we've gotten the hard bit out of the way. We have a lovely clean data set, and we are ready to start building our book recommender. And to do this, I'm going to show you how we can take raw text and turn it into a vector, something that captures the meaning of the text and allows us to compare how similar or different pieces of text are. We're then going to bundle those vectors up into a database, allowing us to efficiently find the most similar books to a query. We'll start with some theory that will help us understand why and how LLMs create vectors, and then I'll show you how you can easily create your own vector database. In this section, we're going to learn how to transform text into a form that allows us to compare how similar documents are to each other mathematically. This has many useful applications, and in this section, we'll see how we can use it to find the most similar books to a query that we have. To start explaining how to do this, we need to understand a basic building block called word embeddings. Now, to understand what these are, let's take 7 words: queen, king, girl, boy, woman, man, and tree. Now let's say we try to manually group them in a 3-dimensional space based on their similarity. So we put woman and man together, we put queen and king together, we put girl and boy together, and off in the corner we put tree. Now if we take the coordinates of each of these words, we can see that along this first dimension, girl and boy are similar, but the rest are quite different. So perhaps this represents something to do with age. On this second dimension, queen and king are similar and different from the rest. So maybe this dimension represents something to do with class or nobility. And finally, in the third dimension, all of the people are similar, but tree is different. So this dimension maybe represents something to do with personhood. These values for each word are word embeddings, and they represent the meaning of a word by grouping words that are similar and creating distance between words that are dissimilar. Of course, we're not going to create these word embeddings manually. That would be a nightmare, especially for large vocabularies. Instead, we rely on word embedding models to do so, which learn these relationships by seeing how words are used in context. So to demonstrate this, I'm going to show you how a model called Word2Vec works, specifically the skipgram architecture. The way this model learns the word embeddings is by taking all usages of each word in your training data and trying to predict which words are likely to surround it. So let's take the case of the word best. We're going to ask the model to predict which word immediately precedes and follows best. So initially its guesses are going to be pretty inaccurate, but as it sees more and more examples of sentence fragments containing this word, it will adjust its internal weightings and these guesses will get closer and closer. So let's get to training this model. In our first sentence fragment, the word in front of best is the, and the word after it is things. In our second example, it's also the and things. However, in our third example, it's the and Halloween. The model is therefore going to predict that the most likely word to precede best is the, and with a little less confidence, the word that follows best is things. The weights that it uses to make these predictions end up being the word embedding for best. We repeat this exercise for every word in the vocabulary, meaning we have a word embedding for each word in our corpus. Due to the way that this model is trained, it means that words that are used in similar contexts end up with similar weights in their embeddings. So you can see that best, worst, and funniest are all used in similar contexts. And when we look at the resulting embeddings, we can see that these three words therefore have similar embeddings. In contrast, words like war, attack, and blast are all used in very different contexts, so they have very different embedding weights on each dimension. Now in practice, word embedding models don't have 3 or 5 dimensions like I've been showing you so far, but they usually have hundreds or even thousands. In addition, we also don't care in principle what these dimensions mean. We only want them to separate out words that are different and group words that are similar. So word embeddings were the hottest thing ever for a while when they first came out. I remember I actually used them at my first data science job and I was completely fascinated by them. However, one of the biggest limitations of word embedding models is that all meanings of a word are collapsed onto the same token, regardless of whether it means different things in different contexts. An example of this is the word bank, which has very different meanings depending on the context. We can see that in 2 different sentences. He checked his bank account describes bank in the sense of a financial institution, whereas the riverbank was peaceful refers to bank as a natural feature. This is where the latest generation of models come in, which are designed to understand the meaning of a word in context. Broadly, they're based on a type of neural network called a transformer model, and all of the cutting-edge LLMs, like the ChatGPT models, Claude, Gemini, Minstrel 7b, and Falcon, are all variations of this type of model. So I'm going to give you a very high-level explanation of how these models work. So let's start with our example sentence. He checked his bank account. So we start by transforming each of the words into word embeddings, just like we did with the Word2Vec model. But we then add positional vectors to each of these embeddings to indicate their position in the sentence. So the embedding for he would be weighted to indicate that it's the first word in the sentence, checked would be weighted to indicate it's the second word, and so on and so forth. These weighted word embeddings are then fed into a mechanism called self-attention. Self-attention basically uses the information from the weighted word embeddings to understand how much attention it needs to pay to the other words in the sentence in order to get the meaning of that word. So let's break down these self-attention vectors. Each word has its own vector. And if we have a closer look at the vector for the word bank, we can see that each of the vector elements corresponds to a word in the sentence. So the first element corresponds to he, the second to checked, and so on. As you can see, the highest values in this vector are for the words checked, bank, and account, indicating that the model has worked out that in order to make sense of the meaning of the word bank in this context, it needs to take these words into account. So you can see that accounting for the words checked and account allow the financial meaning of the word bank to be discovered by the model. As you can also see, the self-attention mechanism tends to focus on the word it's finding context for most strongly. As such, the model creates these self-attention vectors for each word multiple times and then averages over them. Finally, the model does some normalization, which makes it easier to work with these attention vectors. And this process of generating self-attention vectors and then normalizing them is called an encoder block. The attention mechanism allows transformer models to do all sorts of interesting things with text. We can see this with the original architecture of the transformer model, which was designed to translate sentences from one language to another. So in order to do translation between two languages, a transformer-based model needs two components, an encoder and a decoder. As you can see in both the encoder and the decoder, they both use attention blocks to process the text data coming in. However, their goals are a bit different. The role of the encoder is to learn everything it can about how words in the source language relate to one another and send that information over to the decoder. The decoder has a slightly more complex job. It needs to firstly learn everything it can about how words in the target language relate to one another. It then uses that knowledge, as well as what the encoder has sent over about the source sentence, to predict, word by word, the most likely sequence in the target language. So you can see that in this example here. Let's say we have the sentence in English, I have visited Italy. We want to translate it into German. Our encoder will have learned a whole bunch about how English functions, and our decoder will have learned about how German works. Our sentence is then processed by the encoder, and word by word, the decoder will generate the closest matching sentence in German. Over the past 6 years, the transformer architecture has been so successful that it's led to the development of larger and larger models, which are of course called large language models or LLMs. The basic transformer architecture has spun off many different types of models. Some, like the original model, use both encoder and decoder blocks. And we're going to see such a model in the next section of the tutorial. However, many only use decoder blocks. Most of the generative text models you'll be used to using are decoder-only models. And then there are the encoder-only models, which tend to be good for tasks that require a full understanding of the sentence. LLMs are now so big that they're generally too expensive for most people to train from scratch. However, the brilliant thing about LLMs is that due to how they learn during training, they are natural language generalists. They have a deep knowledge of how their training languages work, and they've been used in such a way that they can be adapted to many tasks. And this has led to a proliferation of what are called pre-trained models. These are large language models that someone else has trained and they've made available to the public for use for a downstream task. Here are some examples of pre-trained models. You can see open source models here on Hugging Face, which I'm going to be explaining in more detail in the next section. And here are proprietary models offered by OpenAI. There are many, many different models which have been made available by either large tech companies or research institutes, and the explosion in models can sometimes make it feel overwhelming to get started working with LLMs. However, I hope by the end of this video, you'll feel more confident about these models and how to apply them. In this section, we're going to be using encoder models, so let's have a closer look at these now. As encoder models are designed to understand the meaning of full sequences, such as how all the words in a sentence relate to one another, they're trained with a goal that forces the model to understand this. So let's take the case of a model called Roberta, which is trained by getting it to predict a masked word in a sentence, that is, a word that is missing. So let's see how this training works. Let's say we have our training sentence, I grew up in Paris, so I speak mask and English. Mask, of course, representing the missing word. What Roberta first does is to tokenize this sentence and add these special CLS and SEP tokens to indicate the beginning and the end of the sentence. These tokens are then passed into the model, and the model retrieves word embeddings for each word, weighted by their position in the sentences. These are then passed through a bunch of encoder blocks to get all of those self-attention vectors. The final part of the model uses everything that it's learned about the representation of these words in a sentence to make its prediction about what the missing word is. At the beginning, these guesses are going to be quite bad, again, just like with the word-to-vec model. However, after seeing many different examples of such sentences, the model builds up an internal representation of how the language works and becomes very accurate. The original Roberta model was trained on 160 gigabytes of text, so you can imagine that the models have a chance to build up a really rich representation of the meanings of the words in different contexts. Now, as we've discussed, language models work by transforming raw text into vector representations. So a really interesting thing we can do with encoder models is to pass in a sentence or a document and extract the internal vector representation that the model has made of that sequence. This is called a document embedding, and just like with word embeddings, is a way for us to be able to mathematically determine how similar or dissimilar documents are to each other. So let's return to the example of our books. Let's say we have 4 book descriptions. A heartwarming journey of love and friendship. An ambitious attorney gets entangled in a case which may prove to be more dangerous than anticipated. One of the most meticulous accounts of the decline and fall of the Roman Empire, and a provocative and well-researched take on human relationships. So if we pass each of these through an encoder model, we can convert them into their document embeddings. As each of these descriptions are quite different, the values in each of the dimensions are also quite different, meaning each of these descriptions should be in distinct parts of their embedding vector space. So how can we find a specific book? Well, the first thing we can do is to store each of these vectors in a vector database with some sort of ID, or perhaps some sort of other metadata. You can see that our vectors now have unique IDs assigned to them. So let's say we want to find a book about the Roman Empire because, yes, I do think about that every day. We would first convert this query into a document embedding using the same encoder model we used to create the embeddings in the database. We would then compare this vector with those in the database, calculating a similarity score between the vector and the query. I'm using a distance metric called the cosine similarity here, but there are quite a few different options you can use, and what you have available will depend on the vector database that you choose. So you can see from this comparison, our third book vector, 103, ended up being the most similar to our query vector. However, we don't want to just retrieve a vector. That's not really that useful to us. So this is where the ID comes back in. The ID can be used as a link to the original text of the query, as well as other potential metadata. So in the case of this example, we can use the ID to retrieve the description, and also the title and the author of the book, which turns out to be Edward Gibbon's legendary History of the Decline and Fall of the Roman Empire. So that turns out to be a very relevant recommendation indeed. But you might have spotted a problem. Right now, we're doing linear search. Our search time is going to increase linearly with the size of our database, because right now we're comparing our query with every single vector. So it's not terribly efficient. So to solve this, there are many different algorithms you can use to reduce the search space. And these all roughly work by grouping similar vectors in the database index, meaning that at search time, you're only going to be comparing your query vector to the most similar vectors. However, this grouping is not always precise, meaning that most of these algorithms are a trade-off between speed and accuracy. So you get an idea about how this works from this page from Weaviate, which is a popular vector database company, or there are many such pages that you can read about online. And of course, you don't need to implement these algorithms yourself. The advantage of using a vector database is that they built these into the indexing. And with that big chunk of theory out of the way, we are finally ready to get started building our semantic recommender. So in order to build our vector search, we're going to be working with a framework called LangChain. And we briefly mentioned LangChain when we were installing our dependencies, but I'm just going to dive a little bit more into what it is now. So LangChain is this super powerful framework that's available in Python, and it allows you to do a whole bunch of stuff with large language models. So we're going to be using it for vector search. You can, of course, extend that to make RAG pipelines, but you can also do things like creating chatbots or creating agents. So it's very powerful and it's very sort of state of the art. So another thing that makes LangChain really nice to work with is you're not bound to a single large language model provider. So as I mentioned when we were talking about installing the dependencies, we're going to be working with an OpenAI model in this section, but you can work with any of the proprietary vendors or almost any of them. And you can also importantly work with open source models from Hugging Face. So there's a lot of flexibility there, and it allows you to do a lot of different experimentation and work with a whole range of different models. So jumping back over to PyCharm, you can see from the dependencies that we're importing, the methods we're importing, kind of how the workflow is going to go with creating this vector database. So the first method that we're importing is the text loader. And basically that's going to take the raw text, the text of the book descriptions, and kind of convert it into a format that LangChain can work with. Then the CharacterTextSplitter method is going to split that whole document containing all of the descriptions into meaningful chunks. So in our case, those chunks are just going to be individual descriptions of each book. But in other contexts, you might be splitting a really long document and you might just arbitrarily split it off at, say, 1,000 characters. There are many, many different ways of splitting documents. And if you're interested in this topic, definitely a rabbit hole you can go down. The next step is converting those chunks into document embeddings. And we're going to be using the OpenAI embeddings method to do that and do API calls to OpenAI to use their models to do that. And then finally, we need to store those in a vector database. And we're going to be using Chroma for this. This is a very popular open source vector database, but there are a range of other databases you can use with LangChain, some of them proprietary. So the next thing we need to do is set up our environment so that we can use that OpenAI model. So we're basically going to be calling that model using API calls. So what this means is that we need an API key so that we can connect to our own OpenAI account and be able to charge to our account to use that model. And we're going to get into how to get the API keys and how to basically put credits on your OpenAI account so that you can use those models in a little bit. But for now, let's talk about the nice, clean way of passing that API key to your environment. And my favorite way of doing that is using a package called .m. So what .m requires you to do is first create a .m file. And you can see that here. I just have it sitting in my root directory. And all I need to do is pass in my API keys into this file. Then what I do is I import .m and I import the load.m method. And then I just need to call that load.m method. And what it's going to do is look in the .m file, see those two keys that I have, and it's going to write them to the environment that I'm using for this particular project. So it's very clean and it's very simple. Now that we've done that, let's go ahead and read in our nice cleaned books dataset. So again, we're going to be using pandas to do that. So we import pandas and we're going to call it books again, and we're going to import that books cleaned dataset. So we can see here it is, just as we saw it at the end of the last section. Okay, so now that we've loaded in our data and we've set up our environment, we are ready to start building our vector search. So this is where we revisit that tag description that I created at the end of the last section. And I promised you that I was going to explain why I did this. So when we create the vector search and when we query the database, what we're going to get in return are the descriptions of the books, because this is what's in the vector database. But we don't want to give descriptions to the users of our recommender. It doesn't really make sense. What we want to give them are the titles and the authors of the books. So what we essentially want to be able to do is filter down the data frame that contains all the books to those that were recommended based on our query to the vector database. But doing this based on string match is really messy. It's not a nice way of doing this filtering. It's quite slow and it can be imprecise. So instead, what I've done is I've appended the ISBN as an identifier. And what we can do is when we get back the recommendations, we can split off that ISBN from the front of the description and use that as the thing to filter. So I'm going to talk you through how we do that, but you're going to see that it's quite clean and it's a much nicer way of doing this filtering than trying to do it on a full text match, which is messy and slow. Okay, so the text loader method in LangChain, it doesn't work with pandas data frames. So the first thing we need to do is save these tag descriptions and only the tag descriptions in a text file. So we're going to create some code to do that. We're going to use the toCSV method in pandas. We're going to change that to a text file, and we're going to make sure that it's separated by new lines. And we're also going to make sure that it doesn't have an index and it doesn't have a header. So it's just going to be a file that contains just the text descriptions. Okay, so we can have a look at that text document that we've just created, and we can see that it's done exactly what we needed. We have all of our nice descriptions separated neatly by new lines. So great, now we can start splitting them. So the first thing we do is we load them using the text loader method, and you can see the syntax here is pretty straightforward. And then what we need to do is instantiate the text splitter. So what we want to do is pass a couple of arguments here. The first one is chunk overlap. It's pretty easy to understand. Essentially what it's telling us is we don't want any of these chunks to have any overlap. That's why we set it to 0, because they are separate titles. They shouldn't overlap. And we also set the separator as a new line, so making that really clear. But just going back to this chunk size argument, the reason we're setting that to 0 is because it first tries to look for the closest separator to the index number indicated by the chunks. And basically, if this is more than 1, there's a chance that it may not split on a new line, it will split on chunk size. But so by setting it to 0, we make sure that it prioritizes splitting on the separator rather than trying to split on the chunk size. So now that we've done this, we've instantiated our text splitter, we can apply it to those documents that have been loaded in by the document splitter. And this takes a while, and you can see that we get basically a warning for every single one because we set the chunk size to 0, but we'll just let that run. We will just actually skip over that. And now you can see that it's done. So let's just go ahead and check that that worked correctly. So what we're going to take is the first document of those that have been split using the text splitter. And we can see, perfect, this is the first description. It's just the description. It's worked correctly. So now we can go ahead and we can start building our vector database. So kind of the final step, actually, we're pretty much done, is that we need to, in the same step, create the document embeddings and store them in a vector database. So what we're going to do is to use the chroma method. We're going to assign that to a variable called dbbooks, and we're going to use the fromDocuments method in chroma. And we're going to pass that 2 arguments. We're going to pass it the documents that we created, the ones that have been split using the text splitter, and we're going to tell it what embedding we want to use. And we're going to use our OpenAI embeddings. So what I'm going to do now is take a little diversion and explain to you how you can get access to an OpenAI API key and how you can also load up credits so that you can pay for this model. So let's duck over to the OpenAI website and have a look at that. So in order to start working with OpenAI models, you first need to visit platform.openai.com. And if you don't have an account, you will need to create one. So once you have an account, you can then go up to the top right-hand corner and go to settings, as you can see here, and you will land on your profile page. Now, there are 2 relevant sections for us here. The first is the billing page. So in order to use any of these OpenAI models, you do need to pay for it. But smaller models like the ADA embedding model that we're going to be using in order to create our document embeddings, or older models like GPT 3.5 Turbo are actually pretty cheap to use. So I chucked $10 on my account, I think 6 months ago, and you can see I've still got $4.40 left. So it's not terribly expensive if you're not really hammering these models. So you can see here on this billing page, you can add credit. Like I said, you can load up a small amount. It will last you a while if you're not using the expensive models. And you can also manage your preferences to set things like usage limits. The other thing that we want to have a look at is how you get the API key. And if you just navigate on the right-hand side, you can see that there is a section called API keys. All you need to do is click this green button. It will generate a new API key, and just make sure you save that straight in the .m file so that you can use that. And as you can see, it's relatively straightforward to set up. And once you've got this set up, you've got your API key loaded in your .m file. It's pretty easy and straightforward to work with these models. So now we have everything in place to create our vector database. So if we just execute this cell, you can see that this is going to run for a little while. So I'm actually just going to skip ahead. And you can see that it took about 24 seconds to create that database. So now we're ready to start querying it. We're at the fun part, and you can see it actually wasn't that much work. Okay, so for our first query, let's try for something kind of specific. So let's say a book to teach children about nature. So I'm going to save this to a query variable. And then to get the recommendations, what we're going to do is take our database, the DB books, and we're going to run this similarity search method over it. We're going to pass in that query, and this k equals 10 argument tells us how many results we want to get in return. So let's go ahead and run that, and let's see what it's returned. So if we have a look at the top results, the first one is children will discover the exciting world of their own backyard in this introduction to familiar animals, from cats and dogs to bugs and frogs. And the second one is introduce your babies to birds, cats, dogs, and babies. I'm not really sure why you need to introduce your baby to babies through a book about animals, but anyway, this is still a relevant recommendation. So this is super cool, and it's working really nicely. Recommendations really make sense. But the problem is as I said earlier, this is just returning the descriptions to us. And we don't want to give recommendations of descriptions. We want to give recommendations of book titles and authors and things like that. So we obviously need some way of using these recommendations to filter the data frame containing all of our books. And this is, of course, where those ISBNs come back in that I mentioned earlier. So what I'm going to do is create a piece of pandas code that is going to filter that book's data frame just to the first result that was returned as our query. So the one at the top there, children will discover the exciting world of their own backyard, blah, blah, blah. So let's have a closer look at this piece of code. So we can see in this section here, what we're doing is take the docs, take all of the recommendations that were returned from the vector database, extract from them the page content, so just the text, split that based on space and keep only the first element, so the ISBN, and then strip it so that there's no trailing white space, and then convert the whole thing to an integer. And the reason we need to do that conversion to an integer is because the field in the data frame is also integer. So they need to match in data type, otherwise that matching won't work. And then we pass all of that into a pandas conditional, and that essentially tells pandas, please give me only that book which has this ISBN. So let's see how it worked. So if we run that, it seems to have worked perfectly. We have a book that makes sense, Baby Einstein, Neighborhood Animals. And so this method has worked really cleanly and gives us a really quick and clean way of looking up the books that are recommended through the descriptions. So this is really nice, but we've only done it for one recommendation from one query. So in order to make our lives a bit easier, let's bundle all of this functionality up into a function. So we can do this for every query that we want to do, and it's going to return all of the recommendations. So let's call this function retrieve semantic recommendations, and we're going to give it two arguments. We're going to give it the query, and we're going to give it the number of recommendations we want, the top K, and it's going to return a pandas data frame. Now, the first thing we're going to pass in is the code to basically give us the recommendations. So running that similarity search for the given query against the database. Then what we're going to do is create this blank list This is going to contain all of the ISBNs. And what we're going to do is loop over each of the recommendations that are returned. And for each of them, we're essentially going to do what we did before with extracting the ISBN. I've just made a small change in this function. And the reason why is because I found that for some of the descriptions, they were actually enclosed in quotation marks. And this caused problems when I was trying to parse the ISBN. I couldn't recognize it as an integer. So basically, in this case, what I do is once we have the page content, I strip off the quotation marks, and then I split and keep the first element and convert that to an int. And what we have in return in this books list is a bunch of int ISBNs. And then what we do as the final step is we filter the books data set based on that. So we keep all the ISBNs that match those in the books list. So let's now have a look at how we go with our query, a book to teach children about nature. And these are the results that we get. And they all look great. You know, these all totally make sense. I actually see a Roald Dahl book that I read when I was a kid. So that's actually quite nice. And The Very Hungry Caterpillar as well. So yeah, this has worked very, very well. And this is our first building block for our recommender. And I think you can see that even with the small amount of theory that we needed to cover, this is not terribly complex to understand. And it's very, very powerful and gives you very flexible ways of working with text. So now that we have our basic recommender, let's start thinking about some things we could do to improve it or to refine it. So have a think back to the first section when we were looking at our data set. And remember we had that categories field that was really, really messy. And you might remember that I said to put a pin in it, that we were going to come back to it and tidy it up. Well, this is what we're going to do in this section. We're going to use LLMs to do a technique called text classification that's going to help us sort those categories into a much smaller number of groups. Once we have this smaller number of categories, we can add this to our book recommender as a potential filter. So text classification, as you might guess from the name, is the branch of natural language processing which is concerned with trying to assign text to different discrete groups. So for example, let's say we have this book description that we've seen before, a heartwarming journey of love and friendship. And we might, for example, want to sort it as either fiction or non-fiction. So we could build a text classification model which is trained to do so. And voila, it predicts for us that this book is likely to be fiction. And we can repeat this with each of our book descriptions. This one about the ambitious attorney also gets classified as fiction. Edward Gibbon's masterpiece is, of course, classified as non-fiction. And then finally, our book about relationships is also assigned to non-fiction. Now, text classification doesn't need to be done by LLMs, of course. This is an older problem that we were solving before LLMs. But it does turn out that text classification is something that they're rather good at. There are a few different ways that LLMs can do text classification, but the one we're going to use in this tutorial is called zero-shot classification. What this involves is taking a pre-trained LLM and without any further training, no further work, getting the model to assign text to a category. What we do is we provide the model with a prompt, like the one that you can see on the screen, and the text that we want it to classify. And we may optionally provide it with our categories that we want to classify as part of the prompt. So in the case of our book descriptions, we could take a pre-trained model that is good at doing zero-shot classification and without any further work, instruct it to assign the books to either fiction or non-fiction. So we can see a simplified version of how an LLM might do that here. We have this prompt telling the model to do the classification and what the categories are, and that's all the model needs to either classify it as fiction or non-fiction. So how can models do this out of the box without us doing anything else? Well, it seems to be something that sufficiently large LLMs are able to do, models that are 100 million parameters or more. As we've discussed, transformer-based models are good at understanding which words are likely to be semantically related to one another due to seeing them in a related context during training. So in order to be able to do successful zero-shot classification of our book descriptions, the model will need to have seen enough text showing that certain types of topics are likely to be fiction or non-fiction in its training data. So for example, let's say that we're trying to train an encoder-decoder model. During training, this model will see an enormous variety of text, from Wikipedia articles to news stories to Amazon reviews. And somewhere in that training data, there is likely to be information about books, with information about them such as their categories. So in the training data, the model might see a book that is a moving tale of love, redemption, and family, which is further described as a fiction book. After being exposed to enough similar examples, the model will have a pretty good understanding that books with this sort of topic are fiction. So when we prompt it with the book that we want to classify, the model will be able to compare the book's description with what it's already seen during training and predict that that is most likely to be a fiction book. So we can see that here. A heartwarming journey of love and friendship is similar enough to things that it's seen in the past, so it knows that this is likely to be a fiction. So now that we understand the theory about how LLMs can do zero-shot text classification, let's jump into doing this for our book descriptions. So as we saw in the last section, when we were cleaning and screening the data, we have way too many categories for the books. So if we revisit this and we have a look at it again, what we can see is that we very quickly go from sizable categories, things like fiction or juvenile fiction, down to really small categories that get really specific, things like self-help, computing, etc. And the thing is because we intend to use this for filtering, we don't want too many, but we also don't want each of these to be too small, because what we're looking for is something that's going to facet the recommendations that are returned from the vector search. And that's already going to be a subset of the books. So we don't want to, divide up the categories into things that are too small or too specific. So if we limit this to categories that only have 50 books or more, we can essentially see that we have a number of quite broad categories, including fiction, juvenile fiction, and juvenile nonfiction. So let's go ahead and have a closer look at the juvenile fiction category. We can see, this looks pretty broad. It looks like it really just contains, fiction books for children. So it looks like it could be a potentially useful category. And if we do the same thing with juvenile nonfiction, we can see, a number of books like craft books or educational books for children. So this also could be a potentially useful category. So it's the easiest thing that we can focus on when creating the book categories is by focusing on this fiction nonfiction distinction. So basically what you can see is I pre-created a mapping of the top 12 book categories to either fiction or nonfiction. And in addition, I preserved juvenile fiction and juvenile nonfiction as separate categories, but I've renamed them as children's fiction and children's nonfiction. So for example, you can see that I've changed biography and autobiography to nonfiction. I've changed history to nonfiction, but I've changed things like comics and graphic novels to fiction and drama to fiction. So what this is going to give us is a nice chunk of the data, which is either classified as fiction or nonfiction. And that's going to give us a starter for classifying the rest of the books. So if we have a look at how many of the books now have known labels, we can do this by checking which of the simple categories are not missing. We can see that we have 3,743 books. So this is a pretty good basis, and this is going to form the basis of the data set that we're going to check our LLM-based classifications on. So at the beginning of this section, we talked about how you can get LLMs to do a task called zero-shot classification. That is, you can get them to sort pieces of text into particular categories without having been explicitly trained to do so. So you might be thinking, well, where can I get such a model? Where can I find a model that can do zero-shot classification? And the place we're going to be getting our model from today is Hugging Face. So what is Hugging Face? Hugging Face is a company that has a significant open source branch, and this open source branch is responsible for hosting and distributing all of the major open source LLMs, as well as other types of AI models such as text-to-image, voice models, and multimodal models. So we can see that we're here on the huggingface.co/models page. And on this page, you can see a whole variety of different models that you can use for different tasks. And we go down to zero-shot classification under natural language processing. what we can see is a whole bunch of different models that we could potentially use for our zero-shot classification task. So you might be thinking, okay, well, how can I use this model? And happily, Hugging Face also provides packages for us to interact with these models. And the most powerful one for working with large language models is called transformers. So transformers gives us a whole bunch of functionality in Python for working with open source large language models that are hosted on Hugging Face. And you'll see we're going to use it not only for our zero-shot classification task, but also for our sentiment analysis task down the line. So after this tutorial, you might want to learn more about working with large language models. And the best course I've ever come across for this is Hugging Face's natural language processing course. So if you visit their URL, huggingface.co/learn/NLP course, you will be taken to their homepage. And this course is such an amazing free resource. It takes you through from the basics, how to work with large language models, what the different types of architecture mean, which we have covered a bit in this course, and different ways of working with large language models beyond what we cover in this tutorial. So we've talked about the fact that Hugging Face has these zero-shot classification models that we want to use for our task. But PyCharm gives us a really nice shortcut to being able to choose and access these models. So if I click in a new cell in my Jupyter notebook, and I can also do this if I'm using a Python script, what I will see is a context menu which will give me the option to pick Insert Hugging Face Model. So once we've selected that, we can see that we're presented with this tool window, which gives us the same functionality that we have on the Hugging Face Models page. So if we go over on the left-hand side, you can see that we can filter again by task type. We select, of course, zero-shot classification, and then you can see that we're presented with the same models that we saw on the Hugging Face models page. We can change how they're sorted by likes, by downloads created at or last modified, by the license type, and we can also filter by tags. So we're going to pick the most popular model, the BART Large MNLI. This is a very popular model for zero-shot classification tasks. And we can see that within this tool window, we can also see the model card. And that gives us a whole bunch of useful information about the model, including how to use it. So if we go down to the Use Model button, we can see that PyCharm has inserted some boilerplate code for us to help us get started. And we're going to use this as the basis of our classifier. So having had a look at the model card, it tells us that if we want to be able to use this model for classification, for zero-shot classification, we need to set up the categories that we want the model to be able to classify into. So I've decided to just limit this to fiction and nonfiction. I could have, of course, included the children's nonfiction and fiction, but just to keep it simple, I decided to just limit to the adult classes. So what we do is we set this up as a list, and we include that before we set up our model pipeline. And then one additional change that you can make to this boilerplate code is if your device has a GPU, you can specify that you want the model to be able to use that. So you can see that PyCharm is automatically completing device equals 0. You can use this argument if you have CUDA. I do not. I have an Apple machine which uses MPS, so that is the argument that I will pass in. So I'm just going to execute that cell. And now that that's run, our model is loaded in and ready to start making predictions. Before we start using it, I just want to show you one more thing, and that's the Hugging Face tool window in PyCharm. So if you click on the Hugging Face logo over on the left-hand side of PyCharm, you'll see this tool window pop up. And what you can see that it contains is every single one of the Hugging Face models that I've downloaded. Because what Hugging Face does is downloads and caches models rather than you having to re-download them every time you want to use them. Now, this is great, but one problem that this can lead to is you can see from this size column that the models can be quite big. So it's a good idea to review these models periodically, make sure that any models that you're not using you delete, and that's something you can do right from that tool window rather than having to go to the directory. So let's now get to doing our zero-shot classification. And first things first, let's have a look at the first of the known fiction examples that we have. So we're just going to do this pandas filtering where simple categories equals fiction, take the description. And the reason we add this reset index argument is because when we do a filtering, obviously we're left with rows that have, the index they had in the original data frame. So by resetting the index, we know that we're resetting it so that it's now for the filtered data frame, and 0 is going to be the first example. So let's now run our classifier over that sequence. And you can see that the code here is very, very simple. We just need to pass in the sequence that we want to classify and the categories we want it to classify into. And then once we've done that, you can see it's quite fast. And we get back the labels and we get back the scores. So what this represents is the probability that that particular description, that piece of text, belongs to each of those categories. What we can see is that the probability that it is fiction is much, much higher than nonfiction. So just like the known label tells us, the model has also predicted that this is a fiction book. So in order to actually get the predicted label out of this output, we need to do a bit of post-processing. So the first thing we're going to do is to take that array that contains the scores, and we're going to run NumPy's argmax method over it. And what that's going to yield is the index of the highest probability. And as you can see, PyCharm is telling me we have an error here. It's because I haven't imported NumPy, so I'm going to go ahead and do that. So now that we have that index, what we can do is we can now take the array that contains the labels and take the index of the maximum probability. And if we have a look at that, it tells us correctly that the maximum probability, the most likely label, is fiction. So let's now go ahead and bundle all of that up into a function. We'll call it generate predictions. And it's basically just going to take in the sequence and it's going to take in the categories. It's going to run those predictions, that zero-shot classification, and then it's going to extract the maximum label. So now we set things up so we can get this model to do zero-shot classification over a description and tell us what the most likely label is, fiction or non-fiction. So the next thing we want to know is, how good is this model at actually doing this task? So to find this out, what we're going to do is take a sizable sample of both fiction and non-fiction books. We're going to get the classifier to predict a label, and then we're going to compare it to the known label. So the first thing we're going to do is import TQDM, because that's going to give us a way of knowing how long we've got left in our loop, because it does take a while to do these predictions over 600 examples. And then what we're going to do is create blank lists for the actual categories, the known categories, and the predicted categories, the ones that the model comes up with. Then we set up our for loop with a range of 0 to 300. And what we do is we take examples where the books have the simple category fiction, extract just the description, and basically iterate through the first 300 of those. And for each of them, we generate the predicted category and we add that to our predicted cats list. And then for our actual cats list, we just add fiction. Then let's repeat the same thing for nonfiction. So we change the filtering to nonfiction and we change the actual categories to nonfiction. And then we go ahead and run this. And this is going to take a while. So I'm just going to skip ahead and you'll see the results. So now that that's finished, let's go ahead and throw those two lists in a pandas data frame. And we have these two columns, actual categories and predicted categories. And you can see that PyCharm did a very nice job of predicting what I wanted to type there. And if we have a look at our data frame, we can see actually from the first glance, it looks like it's done a pretty good job. So the next step is to create a column where we compare these actual categories to the predictions and see if they match. And let's go ahead and start creating that. We're going to call it correct prediction. And again, you can see that PyCharm has jumped ahead and auto-completed most of that. I would prefer it to be 1 and 0 rather than true and false. It's basically the same thing, but basically it will be 1 if the predictions lined up and it will be 0 if it didn't. And then the final thing we can do is just check how many of those predictions were correct. And again, PyCharm's going ahead and completing that code. And we can see that we got 78% correct. So this is actually a pretty good rate for zero-shot classification. It does mean we're getting around 1 in 5 incorrect, but for something that is predicting on categories it was not explicitly designed to predict on, this is actually a pretty good rate. So we can be happy with this and we can go ahead and use this model to predict all of the missing categories. Okay, so in order to predict the category label for all of the missing books, what we're going to do is we're first going to create two lists. We're going to create a list for the ISBNs, and we're going to create a list for the predictions. So the reason we're doing this is because what we're about to do is subset the data frame and take only those where the category is missing or where the simple category is missing. And we need the ISBN so that we can actually merge that back into the full data frame later. So let's now go ahead and create that subset of the full data frame. So we use the filtering code to pick only those books where the simple category is missing, is NA, and we keep those two fields, ISBN and the description. And again, we're resetting the index because we want to be able to loop through it and we need the index to be contiguous. So here we set up another for loop. This time it's for the entire length of the missing cats data frame. Then what we do is we take the description, we pass it into our generate predictions function. So we extract the most likely category. And then what we do is we attach that category or we append it to the predicted cats list. And then finally, we attach the ISBN to the ISBN list, or we append it. And then finally, we execute that. And again, this is going to take a while. It's even more than the examples we did for checking the accuracy. So I'm going to skip ahead until this is finished. So again, we're going to chuck that into a data frame. It will have two columns, the ISBN 13 and the predicted categories. And you can see that data frame here. So now that we have that data frame, the last step is basically merging it into the original data frame and using these categories to replace those that are missing. So first step is we're going to use a PD merge to merge those two data frames. We're going to do this on ISBN 13. We're going to do a left join. So the reason for this is because these missing books, these missing categories, are a subset of the original data frame. And we want to be able to keep all the observations. So having the books data frame on the left means that we can keep all the rows when we do this join. The second thing we need to do is, now that we've merged those data frames, there's going to be a new column called predicted categories in the original data frame. So we're going to use a NumPy where clause, where basically we specify that when the original simple categories column is missing, please use the values from predicted categories, the ones that we just predicted. Otherwise, use the original value. And what that gives us is a mixture of the original known labels and our predicted categories. So that's actually going to improve the overall accuracy of this category because only a subset of them are predicted. And then, of course, we can finish up by tidying up and dropping that predicted categories column because we don't need it anymore. So let's now double check that everything has worked. We'll have a look at the data frame. Let's scroll across to this column. We can see that everything looks okay. And when we have a look at our column statistics, we can see that we do not have any missing and we have 4 distinct categories. So everything has worked exactly as we wanted. So doing this zero-shot classification possibly got you thinking, are there other things I could use it for? Are there other categories I could predict? And of course, sky's the limit. If the model was trained on data that actually supports these associations, then of course you can absolutely use it for this. So one potential candidate for us is breaking down that fiction category. We can see that it's 54% of all of our books. So maybe we want to narrow it down to specific fiction types. However, a challenge that we have is having insufficient labeled data to actually test how good these predictions are. So you saw that how with the fiction and non-fiction categories, we had a lot of labeled examples. So we were able to easily see how good our predictions were. But when it comes to specific categories, especially those within fiction, we really don't have a lot of examples in the data. So let's have a look at this in our books data set. We're going to take that raw categories column and we're going to filter it down to those cases where there's an exact match for the following terms. So we're going to use romance, science fiction, and sci-fi as an alternative, fantasy, horror, mystery, thriller, comedy, crime, and historical. And when we run this, you can see that we get a whole 16 observations. So essentially, we really don't have enough labeled data in order to be able to tell how well our classifier will go with more specific categories. So we could still do it, and we could still just assume that the model will do a reasonably good job, but it is a little bit risky. And this is sort of a lesson we need to keep in mind when we're using LLMs. They're not really magic, they're not really different from any other type of machine learning model. We still need to apply the same checks and the same sort of processes with working with them as we would with any other machine learning model. So that's it for the end of this section. We have learned a lot about how we can use LLMs for zero-shot classification. And the final thing we're going to do is, of course, save our nice new data set to file so we can use it in the next section. So far, we've used LLMs to find the most similar books to each other and also to classify those books. Now we're going to use LLMs to do something called sentiment analysis that's going to help us determine the emotional tone of those books. I also think it's a really nice way of showing that the type of data you use can open up the possibilities for different types of features in your data science products. Because we are working with text data, we have the option of extracting sentiment, whereas we're working with a more traditional data set for recommenders, we wouldn't really have this information. So once we've extracted this information, we can include it as part of our recommender to allow our users to filter the books based on their tone. So perhaps someone is after an exciting read, so they might choose something that's suspenseful. Or maybe they just want to be cheered up, so they might choose a book that's joyful. So including this information will allow that additional degree of control for our users. So in this section, we're going to revisit text classification, but we're going to be applying a different technique using large language models. So first things first, what are we doing? Well, we're going to be classifying our text into 7 different discrete emotion categories. We have anger, disgust, fear, joy, sadness, surprise, and of course a neutral category, because sometimes the text will not have any emotional content. So using these categories, we can get an LLM to classify the dominant emotion expressed in our book descriptions. So for example, for this description, our old favorite, Our Heartwarming Journey of Love and Friendship, the LLM is likely to predict that the most likely emotion is joy. Now, of course, we could actually do this emotion classification using zero-shot classification, as long as the data set that the model was originally trained on contains sufficient association between emotional tone and book descriptions. But this time, we're actually going to be doing something a bit different. We're going to be using a technique called fine-tuning in order to get an LLM that can do emotion classifications. So to understand how fine-tuning works and how it's going to give us an LLM that can classify emotions, let's revisit our Roberta model, which we first saw when we were talking about document embeddings. So this Roberta model is made up of a sequence of layers. We have our word embedding layers, we have our encoder layers, and then we have those final layers which allow the model to do that mask word prediction task that it was initially trained to do. With fine-tuning, we can throw away those last layers that were used to do that mask word prediction task, and we can replace it with layers that are instead used to predict emotion categories. What we then do is we take a small labeled data set, and this data set contains text and their associated emotion, and we can further train the model using this. So what you can see is that as part of setting up the model for fine-tuning, we haven't touched those lovely encoder layers. They are still there. We didn't reset them or delete them, meaning that the model has preserved all of that rich information about language that it learned from its original training. What we can use is that information and then the information contained in the emotion dataset to get the model to learn the weights in its new final layer, meaning that we end up with an LLM that is specifically designed to do an emotion classification task. Now, we're not going to be fine-tuning a model ourselves in this video. It's quite complex to do, and it's really a whole topic in its own right to do properly. However, if you want to learn more about how to do this for yourself, in case you want to fine-tune your own model, I'm going to, as always, direct you to the Hugging Face Natural Language Processing course, where they show you in detail in the 3rd section how to do this for yourself. Instead, what we're going to be doing today is use a model from Hugging Face Hub that someone else has fine-tuned and uploaded. So let's get started. So as per usual, I've gone ahead and created a new Jupyter notebook, and I've loaded in our new data set, the one that contains all of those predicted categories. So now that we've done that, let's get to work to finding a fine-tuned model that we can use for emotion classification. So just like in the last section, we're going to be using an open source model from Hugging Face. So we're going to right click in a new Jupyter cell, and we're going to select Insert Hugging Face Model. So as we discussed at the beginning of this section, we're going to be treating sentiment analysis as a text classification problem. So that means we select text classification from the left-hand side of our model selection tool window, and then we can search for emotion in the search bar in order to narrow it down to emotion models. So let's have a look at the most liked model, the most popular model in this category. And what we can see is this is a fine-tuning of a Roberta model, like we talked about at the beginning of this section. But this has been fine-tuned to predict many, many, many different types of emotions. This is probably far more than we really need for our purposes. So let's have a look at the next model. It's also a fine-tuning of a Roberta model. And what we can see is this time it's been fine-tuned for only Ekman's 6 basic emotions. So we've got anger, disgust, fear, joy, sadness, and surprise. And we talked about those at the beginning of this section. And it also has a neutral class. So having a bit of a look through the model card for this, what we can see is just like with our zero-shot classification model, we have instructions on how to use it. So this time, let's actually copy this, and we're going to use this as the basis of how to start using this model. So because someone fine-tuned this model to do this specific emotion classification task, there are likely evaluation metrics we can look at. So how well did this model perform at doing this classification during its training? So I found this page from dataloop.ai, and it gives us a bunch of information about this model. It's quite a well-known model. But if we scroll down to the accuracy section, you can see that it tells us that it had an evaluation accuracy of 66%. And this seems a little bit low, but it is actually significantly higher than the random chance baseline of 14%. That was achieved by taking 100% and dividing it across the 7 different categories. So I think we can be happy with this model. We can feel fairly confident in using it, and we can go ahead and use it to measure the emotional content in our descriptions. So let's first test out our emotion classifier by literally running the code that we copied from the model card. So we have this little example, I love this, which is the sequence to classify. And if we run this, we can see that we get 2 warnings. The first is to tell us that we are not using GPUs when we could be. And the second is to tell us that this return all scores argument that was in the documentation is now deprecated. So let's go ahead and update our function so that we modify these arguments. So the first thing that we're going to do is change this return all scores argument to top k equals none as suggested. And the second is, like we did last time, we're going to add device equals MPS, so we get GPU utilization. So we've loaded in our emotion classification model, and we've seen how we can get it to predict the emotion of different pieces of text. So we now need to decide which level of the description we're going to apply the sentiment analysis over. And we've got 2 options here. We can either get the sentiment classifier to try to predict the overall emotion for the whole description, or we can break it down into individual sentences and try to predict the sentiment of each of these. So let's first look at this first description we have. And let's just start having a look at the potential emotional tone of each of the sentences. So we start with a novel that readers and critics have been eagerly anticipating for over a decade. Gilead is an astonishingly imagined story of remarkable lives. Well, this feels kind of surprising, right? And then we have another sentence. Haunted by his grandfather's presence, John tells of the rift between his grandfather and his father, the elder, an angry visionary who fought for the abolitionist cause, and his son, an ardent pacifist. That almost feels fearful. So you can see that we have a bit of a mixture, and potentially running a sentiment analyzer to get one sentiment or one emotional prediction from this whole description might be losing some information. But let's have a closer look at this. Let's test it out. So let's first run the sentiment analyzer over the entire description. And what we can see is the prediction we get overall is that it's 65% likely to be fearful. Now, I don't really get that impression when I look at this whole book description. Like looking back up a little bit, we can see sentences like, told in John Ames' joyous, rambling voice that finds beauty, humor, and truth in the smallest of life's details. That feels kind of joyous. It feels like this book has a mixture of different themes, and we want to be able to capture those. So, what we're going to do instead is split this description down into its individual sentences and classify on that basis. And very nicely, this classifier actually allows us to classify multiple sentences at the same time. So we can just pass in pretty much the same code, but instead with a split argument that allows us to split that on the basis of full stops. And if we look through this, this is way better. We have a lot more variance. So we can see, just like I suspected, that first sentence is surprising. And if we look a bit further, we've got high scores for other sentences. We've got one that is fearful, and we've got another one that is sad, and we've got another one that is joyous. So we can see that we're getting a lot more variety here, and this is doing a much better job at getting at the true emotional tone of these descriptions. So let's just compare a couple of these predictions to the sentence to see if, it's actually giving the right predictions as well based on eyeballing. So again, let's just take that first sentence again, and let's have a look at the classification. And yes, again, it's mostly classified it as surprising, as we said before. So let's have a look at another sentence. Let's have a look at the fourth sentence. And the predictions that it's given for this is that it's mostly fearful. And this makes sense, haunted by his grandfather's presence. He's talking about a conflict. He's talking about his grandfather being angry. So this all seems to make sense, and it checks out that this classifier is also doing a good job. So this idea does complicate things for us somewhat, because now what we've done is introduced multiple emotions that can be associated with the same book. So how can we make sense of this? Well, my idea is what we can do is for each book, have a separate column for each of the 7 emotion classes. And instead of assigning a category of it is this or it isn't this, what we can do is take the highest probability from across the whole description for that particular sentiment. So for example, if joy is very high in one sentence, but it's low across all the others, we'll just take that higher score for joy for that book description, and so on for all of the other 7 or other 6. So what that means we need to do is we need to process this output of the predictor and kind of amalgamate it or collate it in such a way that it only gives us one maximum score for each of these labels. And you can see with the way this is formatted, we're going to have quite a lot of processing to do. So the very first problem we have is that this output is ordered by the score for each of the sentences. So you can see that we have a different order of labels for every single one of the sentences. So the first thing we can do is actually sort these by score instead. And what it means is that for each of the sentences, we will have the exact same order of each of the 7 emotion categories. So let's create some code to efficiently extract the maximum emotion probability for each emotion for each description. So first thing we're going to do is import NumPy. And then what we're going to create is this list called emotion labels. And this is basically going to be the key in our dictionary. So we're later going to turn that into the columns of a pandas data frame. We also create an empty list for holding the ISBNs. The reason we're doing this is because later on, we're going to create this data frame, as I said, and we want to merge it back in with the full data frame. So again, we're going to use ISBN 13 as the key. And then finally, we create this emotion score dictionary comprehension. What this is going to contain is basically all of the scores for every single description for each of these labels: anger, disgust, fear. So let's now create this function, calculate max emotion scores, in order to extract the maximum emotion scores for each description. So the first thing we do is create another dictionary comprehension. This is designed to hold all of the predictions for a particular description. So we're not talking about every description, we're just talking about a single description right now. Then what we do is we loop over each of the sentences. So each of the sentences returned by prediction. We sort it like we saw before so that all of the keys, all of the emotions are in the same order. And then what we do is we loop over that, and per each of the emotions, we extract the score and we append it using the correct label. Then what we do is we append this to the dictionary comprehension, and then we take the maximum score for each of those emotions. So what we now have for each description is a dictionary containing the maximum probability for each of the different emotion labels. So we now need to apply this function to each of the books. So let's just test it out first. We'll just do the first 10 books. And the first thing we do as part of this for loop is we take the ISBN 13 for that book and we append it to that ISBN list. Then what we do is we take the description, we split it into individual sentences and save that to the sentences variable, and we pass that variable into the emotions classifier. Then what we do is we pass those predictions generated by the classifier into our calculate max emotion scores function. And then we take the resulting dictionary that's returned by that function and we append it to that emotion scores dictionary. So basically by doing that, we should have a dictionary that can serve as the basis of our data frame containing different columns with the maximum probabilities for each book. And if we run that for loop and then we have a look at the results, we can see that it seems to have worked. Like all of these probabilities seem to make sense. If we scroll all the way through, we can actually see that joy prediction for the first book that we already know about. And we know that that's the correct number because we've seen that before. So now that we know this works, let's go ahead and apply it to all of the books. So we're just going to go ahead and copy and paste the code for the for loop from above. And the first change we're going to make is by including TQDM as part of the for loop. So again, we have a progress bar. And PyCharm is throwing an error, so it's telling us we have not imported TQDM. So let's go ahead and do that. And of course, we modify the for loop so that it is now for the length of the entire book's data frame. Now, of course, we are starting from scratch with this loop. So we don't want the results from the previous run to be saved to the ISBN or the emotion scores variables. So let's just go ahead and copy and paste the three variables from above down here. So we've got emotion labels, we've got ISBN, and we've got emotion scores, and they're basically going to be reinstantiated here. And pretty much this is it. We are good to go. So let's just kick that off. And again, this is going to take quite some time to run this over more than 5,000 observations. So I'm just going to skip ahead and we can now have a look at the results. And with that done, let's now pass the results of this dictionary into a pandas data frame. And we don't want the index to be ISBN, but what we are actually going to do is create a separate column for ISBN and assign the ISBN list to that. So if we have a look at that data frame, we see we have exactly what we wanted, got a separate column for each of the emotions, and we can see that each of those columns contains the maximum probability for that description. Now, of course, the final thing that we need to do is to merge this back into the book's data frame. So again, we're going to use pandas merge. We have the books, we have the emotions data frame, and we can just merge them both on ISBN 13. And so let's now have a look at the resulting data frame. And if we scroll across, we can see all of our emotions columns. And if we actually want to have a look at the distribution of those emotions, we can again use the column statistics function. And what we can see is we actually have a pretty good distribution of most of the emotions. And in particular, the sadness emotion has quite a lot of pretty high probabilities. So this indicates to us having a look at this that we do have a relatively good range, even though we do have, some inflation at the lower areas. And this is going to give us a pretty good variable to use for sorting the different books when it comes to making the recommender. And then, as always, the final stage is to save our beautiful new data frame to file so we can use it in our final step, which is to present all of this in a dashboard. So we're going to go ahead and do that. And I hope this has been an interesting overview of how large language models can do sentiment analysis and given you some ideas on how you might be able to use this in some of your projects. So now we've finished developing all of the different components for our book recommender. We have our vector database that allows us to find the most similar books to a query. We use text classification to sort the books into fiction or non-fiction, meaning our users can also filter books based on this category. And we found out how likely each book description is to have a certain emotional tone. However, all we have right now is a bunch of code and a dataset. Admittedly, a very nice dataset, but still, it's just a dataset. It's not the most user-friendly interface. As such, the last thing that we're going to cover is how we can bring all of this together and present it in a dashboard that people can use to get their book recommendations. So in order to build this dashboard, we have moved away from Jupyter Notebooks and we're now working with a Python script. And if you want to create a Python script in PyCharm, it's the exact same process as creating a Jupyter Notebook. You just need to pick Python script instead of Jupyter Notebook. So to get us started, I've already gone ahead and imported all of our dependencies. These should mostly look familiar because we've already covered them in the previous section. So we have pandas, numpy, and .m. We have our LangChain packages, and the only new one we have here is Gradio, and I'm going to cover that in a second. We've already added our load.m function in order to load our OpenAI API keys into the background, and I've gone ahead and read in our very latest books data frame, the one that contains all of those emotions that we just added. So let's now talk about Gradio. So Gradio is an open source Python package that allows you to build dashboards specifically designed to showcase machine learning models. So it's really tailored nicely to allow you to use things like machine learning models or LLMs under the hood. And if you go to gradio.app, you can explore a lot of the very, very powerful functionality that it has. And we'll see a touch of it in this. You can see that it can be quite flexible in terms of the things you can show, but it gives you a really cool way of demonstrating the things that you're building with code to people who may not necessarily want to use code in order to use your models or whatever else you're creating in Python. So first things first, we're actually going to be using the thumbnail as part of our dashboard. And the thumbnail is basically a little preview of the book's front cover, which is going to give us a nice sort of visual element to our dashboard. So the books dataset that we use provides a URL which links to Google Books. But what that provides us by default is book covers that are all kind of random different sizes. So what we actually want is that Google Books returns to us the largest possible size that it has available so that we get a better resolution. So we can add this little argument to the end of the URL, just appending that to the string, and that's going to give us back much better resolution book covers. The next problem we have is that a number of books don't have covers. So if we try to render them, we're actually going to get an error. So what I've done is I've gone ahead and I've created this interim cover. I will provide this as part of the repo with all the code for this project, but you can use whatever you want. And basically what we now do is we modify the code, again using npware. And what we're going to do is replace those cases where we have a missing cover, so where large thumbnail is an A, with this interim cover. And otherwise we'll use the link that's provided. And that's it. So we're now ready to use the thumbnails so we can get on with building the next parts of our dashboard. So the next thing we need to do is add that code that we created in the second section in order to build our vector database. And this is so we can, of course, do the core functionality of our recommender, which is semantic recommendations. So just to remind you what this code does, in this first line, what we're doing is reading those tag descriptions into the text loader. Then we're instantiating a CharacterTextSplitter, which has as a separator the new line. Then we're applying that to each of the documents. So what we end up with are document chunks that are individual book descriptions. And then what we do is we convert those into document embeddings using the OpenAI embeddings, and we store those in the Chroma vector database. So now we're going to create a function that's going to retrieve those semantic recommendations from our books data set And it's also going to apply filtering based on category and sorting based on emotional tone. So let's go ahead and start creating this. Let's call it retrieve semantic recommendations. And it's going to have as its arguments the query. It's going to have the category, and we can set none as a default, and also the tone, which again can be none. And then we're going to have 2 top K categories. We're going to initially retrieve 50 recommendations because we're going to apply some filtering. And then what we're going to have is a final top K, which is going to be limited to 16, because 16, as you will see, looks quite nice for display on our dashboard. And then, of course, the result that it's going to return is a pandas data frame. So to start this function, we're going to, again, repeat some code that we saw all the way back in the second section. The first thing that we're going to do is get our recommendations from the books vector database, the DB books, and we're going to limit that to the initial top K, those top 50 results. And it's going to be based on a query that's going to be input by our user. Then what we're going to do is get back those ISBNs of those recommendations by splitting them off the front of the descriptions. And then what we're going to do is limit our books data frame to just those that match the ISBNs of those books recommended from the vector database. And then what we're going to do is start applying some filtering based on category. So basically, we're going to have a drop down on our dashboard, and it can either read all, or it can read one of the 4 simple categories: fiction, nonfiction, children's fiction, and children's nonfiction. So basically what the argument to be is that if someone has picked anything other than the default all, we want to filter the books recs data frame down to only those books that match that category. And otherwise, we just want to return all the recommendations. And then you can see what we've done is we've limited those filtered recommendations down to the final top K. And then finally, the way we're going to use the emotions category, I think I mentioned this earlier, is we're going to sort based on the probabilities rather than doing any sort of classification or filtering. So say if someone picks happy as a label that's going to match to joy, then what we will do is sort those recommendations based on the highest probability of them being joyful books. So we're going to do this for 5 of the emotions. We're going to do it for joy, surprise, anger, fear, and sadness. And they're going to correspond to a drop-down menu with labels happy, surprising, angry, suspenseful, and sad. So I decided to leave out disgust because I can't imagine anyone really wants to read books that are likely to disgust them. And I also left out neutral because neutral is kind of implied by all. So, you're not really looking for anything specific. So let's go ahead and create the code for that. So what you can see, again, it's just a simple if else clause. So if tone equals happy, then sort these books based on joy and make sure that it is descending. And then do the same for the others. And then to end this function, we just return the data frame with the book recommendations. So the next thing we need to do is to create a function that specifies what we want to display on the Gradio dashboard. So we're going to call this recommend books, and it's going to take 3 arguments. It's going to take the user query, it's going to take the chosen category, and it's going to take the selected tone. And what we're going to do is first get our recommendations data frame by calling that function that we just created, retrieve semantic recommendations, and we're going to pass in those 3 arguments. We then create this empty results list. And what we do is we then loop over every single one of these recommendations that have been passed back from our previous function. So the first thing we're going to deal with is the book description. So this is just going to be the description field, of course. But the thing is we're going to be using this on a dashboard that has a limited space. So we don't necessarily want to show the full description. So instead, what we're going to do is we're going to split that description into its separate words. And if the description has more than 30 words, what we're going to do is cut it off and just make it continue with a trailing ellipsis. So let's now think about how we want the authors list to be displayed. So in this data set, if a book has more than one author, they are combined using a semicolon. So first things first, we're going to take the string containing the authors and split it on semicolon. So let's now think about the different conditions. We might have a book that has two authors. So let's create an F string that separates these two authors using AND. So we have the first author in the first placeholder and the second author in the second placeholder. Or we might have a book where we have more than two authors. So in this case, we create an F string where all of the authors except for the last author are separated by a comma, and then the last author is added on using an AND. Or else we just have a book with one author, in which case we just use the author. And you can see I've just made a small mistake here in the F string for two or more authors. I need to use single quotation marks rather than double quotation marks. So I'll just pop up and change that. So the way that we're going to display all this information about the book is as a caption that's sort of appended to the bottom of the book thumbnail image. So let's now all combine this into a caption string, again using an F string. We'll first have the title by authors, and then colon, we have that truncated description. And then finally, we have that results empty list that we created earlier. So what we append is a tuple containing the thumbnail and the caption. And we're going to do that obviously for every single book, looping over it using that iterRows functionality. Okay, so we are now ready to finally start creating the dashboard. And you can see actually there really wasn't that much code we needed to write to get to this point. We could have actually been a little bit less fussy about how we presented the caption, but you'll see it will look very nice. So you'll see it's worth the effort. So the first thing we do is we create two lists. The first is our list containing all of our categories plus that all category that I talked about earlier. And then we do a similar thing for tone. So if someone doesn't want a particular emotional tone, we have all as a stand-in for neutral. So we start off our Gradio dashboard with the following code. And you might have noticed as I'm writing it, I'm including the argument theme within the blocks method. So Gradio actually allows you to customize dashboards to an extent with a bunch of different themes. So before we go any further, let's quickly go and have a look at what they are. So we can see that we are on the theming guide page within the Gradio documentation. And if we scroll down a bit, we can see that these are all the themes that are available. So they range from themes that are very simple up to themes that are a bit more bright and a bit more colorful, like the citrus theme. So I specifically chose the glass theme because when I messed around with the different themes, this really felt like the most dignified, something you might want for a book recommender. But depending on your purpose, you might want something very simple, very soft, very bright. So you can just play around with these. So continuing on with our dashboard, we can see that the first thing we include is this markdown element. And this is going to be the title of our dashboard. So this will appear at the top and it'll tell people what our dashboard is about. So we will call it Semantic Book Recommender. So now we're going to create the part of our dashboard that our users will be interacting with. So this is going to first contain our user query, and we'll represent this as a text box. We're going to give it the description to please enter a description of a book. And we can actually add a placeholder, which is really cool, to give them an idea of what sort of things they can actually query. So let's say we put, for example, a story about forgiveness. Then what we're going to do is we're going to add drop downs for both category and tone. So let's first have a look at the code for the category dropdown. So we use this dropdown method, and what we do is we assign the choices by assigning that list with all the categories. And again, we can add a label and we can make the default value all. And so we do the exact same thing with the tone dropdown. And then finally, we need to add a button so people can get their recommendations. We use the button method to do that. And again, we can label that. So what we're now going to be doing is adding the functionality to display the recommendations. So again, we use that markdown method and we give it the subtitle recommendations. And we're going to be displaying it as a gallery. So this is going to be a really nice way to showcase all of those nice thumbnails of the books that we prepared. And what you might have noticed is I've made it size of column 8 with 2 rows. This is why we have a maximum of 16 recommendations that are returned after filtering. And then finally, we need to tell Gradio what to do when users click that submit button. So what we tell Gradio to do is to execute the function recommend books, take as the inputs the user query, the category dropdown, and the tone dropdown, and to output whatever comes out of that recommend books function. And then finally, of course, we create our main method, and from there, we can execute the script. So as you can see, this is rebuilding the vector database from scratch. We can, of course, just save this vector database because we don't really need to recreate it each time. And that means that it's going to be a lot faster for our dashboard to start. And then finally, our dashboard is launched. So let's go ahead and have a look. So here's our Gradio dashboard. So here are all the elements that I described we were creating when we were coding it up. We can see our text box where our user can enter their query with that placeholder that we designed. And we can see our 2 dropdowns with category and emotional tone. So let's go ahead and do our first query. And let's make it pretty broad. Let's say a book about World War I. So when we click find recommendations, we get back that really nice gallery with all of the different thumbnails. And you can see the cover not found popping up a couple of times. And if we go ahead and click on the first of the books, we can see that caption that we created being displayed down the bottom. So you can see why I needed to truncate the description. There's not very much space. And if we just go clicking through down the bottom, we can actually scroll through the gallery this way or scroll through it on the main screen. So let's now try our category filter and let's filter this down to fiction books. And you can see that this has eliminated a lot of books that were about World War I, but were not actually fiction stories. So let's now try sorting these books based on their emotional tone. And well, we're talking about stories about World War I, so they're probably going to be sad. So let's try sorting on that. And basically what we can see is the top recommended one is this Virginia Woolf book. So this is what our recommender has come up with. But searching for books about World War I is pretty straightforward. So let's put our semantic recommender to the test and let's try something a little more nuanced. So let's say a story about a troubled family set across many generations. So looking at this second result, we can see, pretty good. So the description is a young widow raising 2 boys. Sarah Larden is struggling to keep her family together. But when a shocking revelation rips apart the family of her closest friend, looks pretty relevant. This one here also looks pretty good. Bryony Ashley knows that her family's grand estate is both hell and paradise. Once elegant and beautiful, yet mired in debt and shrouded in shadow. Looks pretty troubled to me and deals with this sort of generational family issues. And actually, if we go ahead and we sort this list of recommendations based on how suspenseful they are, this one actually comes up at the top. So that seems pretty consistent. Like this book seemed like it was probably going to be like a good mystery as well as a family generational drama. And this brings us to the end of the tutorial. Thank you so much for completing it with me, and I hope you've enjoyed it. So let's end with a quick recap. In the course of this tutorial, we've covered a lot of different topics in modern natural language processing. The core of this tutorial was, of course, large language models. And I hope you've ended this tutorial with an understanding of how these important models work, as well as how flexible their applications can be for solving natural language problems. We've also seen the current state of the development ecosystem around LLMs. And we've seen how getting access to and choosing between these models is getting easier and easier. We saw how proprietary providers like OpenAI have their own easy-to-use APIs to let you access their models. And these can be relatively inexpensive depending on the model you use. We also saw how Hugging Face Hub makes it easy to find and choose between open source large language models, and how PyCharm's integrations with Hugging Face make it even easier to do that within your development environment. Finally, user-friendly Python packages such as LangChain and transformers make it easy to do even relatively complicated tasks like building a vector database with really just a few lines of code. So just before we wrap up, there are a few things that I wanted to remind you about that I've mentioned throughout this tutorial. The first is if you want to get that 3-month free license for PyCharm Professional, make sure you grab the code from the description below. If you want to ask me any questions or contact me about this tutorial, you can also find my social media links in the description as well. And then finally, I have shared some further resources in the description if you want to follow up and learn more about this topic after this tutorial. So thank you again so much for joining me, and I hope you had as much fun as I did. I hope you're feeling confident and excited about working with LLMs after this tutorial. And I also hope that you're feeling inspired to learn more about natural language processing. It is a very exciting area of data science, and there's a whole lot more that obviously I couldn't cover in this tutorial, which is waiting for you to learn about. Please keep in touch. I would love to know what you end up building.